Thank you all for coming. My name is Shawn Jones, and today I'm going to be talking about avoiding spoilers on MediaWiki fan sites using Memento. And so, I just want to give you a heads up warning, this presentation may contain spoilers. So there are some examples. It all started with this guy from Game of Thrones. We were at work, me and a group of other people who watched the television show, and it became apparent that some of us had seen the episode from the night before, but others had not. And so we couldn't continue our conversation about the episode, but we still wanted to talk about Game of Thrones. So we turned to fan wikis to go ahead and continue our conversation, look things up, and keep talking about the characters that we were interested in and events that occurred. And they're useful to our discussion. Unfortunately, the current version of the page has spoilers on it. He was. What do you mean he was? The people who hadn't seen the episode still thought he is. Deceased. Well, now we know what was means. How he died. Even more information about how he died. And then things that happened after he died. So the thing is that some of us enjoy fiction so much that there are fans that create these wikis, these fan-based wikis for the shows, and the rest of us fans read them. And so what if we could avoid these spoilers by using past wiki pages? How do we get to the point where Joffrey's still alive? As much as many of us Game of Thrones fans might want him to be dead, he's still alive. So we're going to cover some background. We're going to discuss a little bit of related work. We'll discuss a concept called a TimeGate, which is a part of Memento, which I'll talk about also, which is how you get redirected to past versions of web pages. We'll discuss our theory of spoiler probability. We'll measure spoiler probability in some websites, in some fan-based wikis. We'll discuss the Wayback Machine. And the point of this is to show that the way that the TimeGates are currently constructed, or the heuristic that they're currently using, isn't sufficient for avoiding spoilers. So we have a solution in the Memento MediaWiki extension. And then we'll finish up with future work and conclusions. And so first we're going to cover some background. Most of us are familiar with the web browser and HTML. HTML is what most web pages are written in. The web browser renders the web page for us. HTTP, the Hypertext Transfer Protocol, is what delivers web pages to your web browser. It consists of an HTTP request that goes from the user agent or web browser to the server, and then an HTTP response which comes from the server back to the browser. This is what an example HTTP request from Google Chrome looks like. This is one that I pulled right off the browser. And the interesting parts from this, the salient parts, are basically these two lines at the top say, give me this page about the Hunger Games from Wikipedia. Wikipedia then responds with a response here with a series of headers. And the interesting parts here are, there's a status code at the top. There's 200 OK, which means OK, I have what you're looking for. Other status codes you may be familiar with are 404, which means I can't find what you're looking for. There's also 500, which means the server broke. And then there's 302, indicating that I'm going to redirect you somewhere else. Also, another interesting thing is this content length here indicating how big the page is. This last modified header indicating when it was last changed. And then there's this new line indicating the start of the actual HTML. And because it knows the content length, it just keeps reading. The browser keeps reading until it reaches that number of bytes. Now, introducing a little bit of web architecture here, we see that resources are identified by URIs. And resources have multiple representations. In this case, our resource is an article about the character Buffy the Vampire Slayer. And you have an English XHTML representation, a Spanish HTML representation, and a Chinese PDF representation. And so the idea is that we can get to each one of these representations separately, but it's kind of, I want to say, magical in the way that they're delivered. And these different representations have different dimensions, such as time, language, content type, things like that. And they are delivered to the client and reported by the server using a series of headers. And these headers define the content type, language, and so on, and they were specified in RFC 2616. Their updated specification, just updated last year, is in RFC 7231. The term for this is called content negotiation. And the interesting thing is that it works so well, most of us are unaware that it's working. You download a browser, it knows what language you downloaded the browser for, and so it tries to find pages in that language. The same thing for the content type and the character set and other things. Now the other point I wanted to bring up is that content negotiation doesn't just create these representations out of nothing, it just redirects you to ones that already exist. So using our headers example, we see also that these additional headers are indicating from the browser to the server, I prefer that you send me a page with this image format, compressed with gzip, and in US English. And the server goes ahead and responds with, well, I found you something that's compressed with this format, it's in English, but the best I could do was HTML. And this is how content negotiation works. Memento finally completes this set by including time. Remember the other dimension that Tim Berners-Lee was talking about. RFC 7089 defines Memento, allowing us to negotiate in time. And the way Memento works is you have 3 steps. You start off here with the client contacting the original resource, the regular web page that you would go ahead and normally talk to, and it's looking for this little link header here indicating that there's something called a TimeGate associated with this page. Then it takes that URI from that link header and uses it to visit the actual TimeGate, which is another resource whose job it is to redirect your browser to archived web pages. Then the response from that has a location header which indicates where the browser should go in order to find an archived web page, also called a memento. So from the first step, we see that most servers don't yet return all this data. This link header, only some servers return that. So Memento clients default to known time gates that exist on the internet. We also see that they use a GET request in order to access the time gate. So this GET request looks like this. You have a GET, and then the URI that they want, and then this header called accept datetime indicating the datetime that you want, essentially, for a given page. And then the TimeGate responds with a 302, which means don't stop here. I'm redirecting you to go somewhere else. So the interesting thing about the TimeGate is that in addition to that, you also have this location header which tells it where to go. And then, like any other request, the browser just goes ahead and grabs the final memento like it's any other web page. Different for the memento is this header here of memento datetime indicating the datetime that the web page was captured or saved or recorded. And there's also a link header here containing a bunch of information about other archived pages for this resource. Memento also provides time maps, which are machine-readable lists of mementos with the date times. And time maps are useful for time gates and other resources in order to try to perform this, what we call datetime negotiation. Memento for Chrome is, and we'll see that in a little bit, Memento for Chrome is a Chrome extension that lets users right-click into the past. You select a date and time, you visit a web page, and then you can right-click on that web page and visit previous versions of that web page. The neat thing about it is that you can click on links in that web page, or right-click on links on that web page, and continue to browse the web as it looked in the past. Mink is an alternative that lets users see all mementos for a page. So you go to a page and you have this little UI widget that shows up at the bottom, and you have a drop down here that has a series of mementos that you can choose from for that particular page. These are alternative ways of experiencing the past. Now, we've talked about Memento, we've talked about time gates, but who maintains these mementos? Who takes care of these archived pages? Well, back in the 90s, the Internet Archive started up recording the web as best it could, and so now the Library of Congress and Archive-It and all of these other organizations have gotten involved, and they all have their own web archives. The neat thing about Memento is Memento provides you one place to go to in order to get the appropriate archived page for your datetime from all of these. So how are mementos acquired? Well, you have a crawler, and what the crawler has is this list of URIs called a link heap, or others call a frontier, and the crawler just pulls the first thing off the top, and then it goes and requests that particular web page or whatever that URI is identifying, parses it if it's HTML, extracts the links, the images, and any other embedded resources, and then just puts them back on the link heap. And it keeps going around and around and around, and this is how it continues to archive the web. The Internet Archive provides the Wayback Machine as a way to graphically view mementos. And the neat thing about the Wayback Machine is you can put in a URI, and it gives you a list of all of the date times for a prior web page. As you select one of those, and you see a previous version of a page. This is powerful stuff. This was actually used last year to prove, or not prove, but support the theory that Ukrainian separatists shot down a Malaysian airliner. This is powerful. We're not going to use it for that. The Internet Archive contains mementos for wiki pages as well. So here's a page about Abraham Lincoln. So this is a page from 2004. The current page looks like this, so you can see how it changed. But the interesting thing about wikis is that wikis are edited by multiple authors, many authors over a period of time. Now these authors all produce many revisions, and the nice thing about wikis is they keep every last revision of a page. So those of you who have listened to me talk about this or are following along very closely see where I'm going. And so the nice thing about it is that you can actually visit these old revisions of pages. The older versions of pages have this nice little header indicating they're an old revision, but for the most part the text is all the same as it was. So for a wiki, if you look at these two timelines here, you'll see that a wiki consists of a series of revisions. And the Web Archive comes by and creates a series of mementos from those revisions. You think of this as the Web Archive is sampling the wiki. Another interesting thing is we also know which revisions were missed. We call them these missed updates, and we'll go ahead and cover these. We'll talk more about these later. So I want you to consider the timeline of every episode in a series. Think about these dots here being episodes. Now consider the timeline of wiki revisions created by fans from those episodes. Now consider a third timeline of the Web Archive coming along and recording these revisions. Now, Steiner noticed that events inspire wiki revisions. Or in our case, episodes inspire wiki edits or revisions. And so from this we see that episodes lead to revisions, which eventually lead to mementos. And this brings us to what we call the naive spoiler concept. Revisions after the episode air likely contain spoilers. Revisions before likely don't contain spoilers. So what we want to do is we want to allow you to select a date time prior to the episode you haven't seen and get back into a world where Joffrey's still alive. This might terrify you, but it's where you want to be because you don't know he's dead yet. So we'll cover a little bit of related work because we're not the only people who are trying to solve this problem. Others have tried to solve the spoiler problem with spoiler alerts and spoiler notices. They try to hide text in web pages. You highlight it and it's revealed. They click on it and it's revealed. Others block social media posts based on input. There's been academic studies. Most of them have dealt with social media, but the important thing that these folks found in the academic studies were that fans would actually avoid social media, web pages, and TV shows because they didn't want to see spoilers. Now, if you're looking for an actual financial reason to avoid spoilers, you have lost ad revenue. You have advertisers who aren't getting what they paid for because people are afraid to look at the web page because you put up a spoiler notice. So our goals are to work with wikis, not social media. We don't just want to warn the user. We don't want to hide the data. We want to make sure the resource is still useful. We want to show the resource as it existed prior, and the advertisers can still have their ads. So we're going to show how TimeGates, for the most part right now, are unable to solve the problem. If Memento just worked the way we expected it to, then we would already be good to go. This is why it's a thesis. So TimeGates can be represented by an equation. And if you consider the stylized G to be the function of the time gate, you have the URI that you want, the previous version of, and you have the accept date time or the target date time or desired date time as a second input to this function. You can get the memento. Now the interesting thing we've added here, and this comes from Ainsworth's paper, this equation anyway, the thing we added was this H here. This H indicates the heuristic that you're using. And so there are multiple different heuristics you can use for time gates. The most widely used one is called min-dist, or just minimum distance. Now this is the easiest one to use. You just have your target date time here on this timeline, and you pick the closest memento to it. Now the problem with this, obviously, is that sometimes it leads to spoilers. You end up in the future because the future memento is closer to the target date time that you've chosen. Remember, you're going back into the past, you're giving it a date time that's looking across all the mementos that it's recording. So some might say, why use this at all? Why not use another heuristic? And the reason is that if you have a sparse archive, where you have, say, a memento from 2003, and another one from 2008, and you go ahead and choose a desired date time of 2007, for most uses, the 2008 memento is going to be better than the 2003 one. So for a lot of applications, this is good enough. We're suggesting minpast, where you use the minimum distance in the past. You use the desired date time as an upper bound. And you only choose the closest mementos that don't go over that. Minpast never has spoilers because the upper bound basically blocks the time gate from choosing it, considering anything past it. And then oppositely, you have min-future, which selects basically the lower bound is the desired date time that you specified. And using min-future, you always get spoilers. This has its own applications. There are several other heuristics here. Min-near is where the bounds can be specified by a system or end user. You have equal past, where it compares the content, the mementos on either side, and favors the past one. Equal future, which is the opposite of that. Sim past and sim future, which use a similarity metric instead of just looking at the content and seeing if they're equal. And so we compared all of these heuristics and came up with some potential running times. If you go ahead and read the thesis, you'll see an example algorithm. And we found that these last four, because they're comparing the content, are too expensive, really, compared to the others. So we've come to the conclusion that minpast is the best for avoiding spoilers. So now that we have a vocabulary to work with here, minpast, min-dist, different heuristics and everything, and we've talked about how min-dist is used most of the time for sparse web archives. How bad is the problem? Well, let's see. Again, consider our first timeline here with the 3 episodes, and consider another series of wiki revisions that are created based on those episodes, and consider a series of mementos that are records of those revisions. And also remember our naive spoiler concept where we want to select a date time prior to the episode we haven't seen yet. We end up, when using min-dist, with something that we've called a spoiler area. And if you take these three timelines, and because we're using min-dist, minimum distance being that anything past the halfway mark between the two mementos results in you going to one side or the other of that halfway mark. The area between the halfway mark and the episode is where you get directed to the future, even though you're selecting date times prior to the episode you haven't seen yet.
So Shawn, go back there and walk through that example again. Choose a particular point to a T, some.
So say you were to pick T10 here. T10 exists prior to the episode. T10 is a date time. If you pick T10, you'll end up with at this memento, which refers to this revision, which occurred after the episode aired. So based on our naive spoiler concept, this revision would contain spoilers. It's likely to contain spoilers if it's right after the episode. So that's the whole point of this red area. So looking at these three timelines, we see that there's a variety of conditions that can result, and we've put them into categories of pre-archive, which exists before the first memento is recorded. You have archive extant, which occurs after archiving started, and you have post-archive, which occurs after the last memento has been recorded. Sometimes archiving stops for a variety of reasons. And actually, one of the things we won't talk about post-archive a whole lot, because after the last archive, using min-dist, you'll always get redirected to that memento, which existed before the episode. So it's always going to not contain spoilers. So pre-archive spoiler areas exist for, say, episode 3 here, when you have somebody select a date time prior to the episode, but archiving hasn't started, and so the minimum distance from any date time in here, in the red region, leads you to the first memento, because it is the shortest distance. We also came with this equation here for describing these pre-archive spoiler areas. Now, contrary to this, for say episode 3 here, you have what we're calling a pre-archive safe area. Archiving hasn't started yet, but this revision here comes before episode 3, so there's no spoiler area for episode 3. Now you'll notice that there is still a red area on this chart, and that's because that's for episode 2. Episode 2 still has a pre-archive spoiler area, because if you're trying to avoid spoilers here, you'll get the memento that's after the episode 2, but more importantly refers to a revision, which is after episode 2. And you see this is the second condition that's in our equation. Finally, as I showed earlier, you have archive extant spoiler areas, which exist after archiving has started. And so we've come up with this equation to describe them. Again, you're after the halfway mark, but before the episode, and somehow, even though you're before the episode, you end up at a memento that refers to a revision after the episode aired. So it probably contains spoilers. There's also several situations where you don't get spoilers. I'm only going to cover 2 of these. You have a situation where the revision follows the halfway mark, but the episode doesn't. So if you try to avoid spoilers for this episode, you're going to end up back here, which existed before the episode, so no problems. And the same thing, and with this guy here, it's not the episode so much, but the revision comes before the episode, so there are no spoilers. There are 4 others of these. If you want more information on them, we can talk about them, and they're also in data. So the whole point of this was to calculate probability of encountering a spoiler using min-dist. And so we came up with the idea of a potential spoiler zone between the first episode and the last episode in the series. If you're trying to avoid spoilers for the last episode of the series, you're going to select a date time prior to this line. So anything after this, you're obviously not trying to avoid spoilers. And if you're trying to avoid spoilers for the first episode, well, it hasn't aired yet, so it's kind of hard to choose anything over here. And that's why we came up with this. So if you combine these spoiler areas with a potential spoiler zone, you can calculate probability of encountering a spoiler for a web page, or for a wiki page. So what we do is we take the number of seconds between the first episode and the last episode, we iterate through all of them, and we count the number of times that we encounter one of these spoiler areas. And then we divide that by the whole region itself, and this gives us the probability of encountering a spoiler using min_dist. So now that we've got this theory that these spoiler areas exist, how bad is this problem? So 16 lucky wikis were selected from wikia.com, and unfortunately we found out that not all of the pages were in the web archive. So if you're going to use the Wayback Machine or the web archive to try to browse for your favorite fiction, 38% of the pages actually aren't there. So they're missing. So already we're kind of starting off with a little bit of a deficit. But for those that did exist, we took the revisions from wiki export pages, we took episode dates from epguides.com, and we took mementos from the Internet Archive time maps. Remember the time maps that I talked about before, and we fed them into the equations we came up with, and we calculated what the spoiler areas are. And what you end up with is that spoiler areas do exist. This is an actual problem. This is a page for a character named Sheldon Cooper in The Big Bang Theory. And you see, if you try to browse this wiki, and you pick a date time in any of these areas, you will end up in the future of that episode. Now, how you read this is, you see how the episodes bunch up on our first timeline here. That's what seasons look like. And down here, you'll notice that there's fewer mementos recorded here, which result in fewer chances of spoilers. Now, I think we'll all agree that archiving less is not what we're aiming for here. But it's just an interesting scenario, even though there's plenty of wiki edits to choose from here. And so we discovered there are different categories of pages. We call them normal, wiki before show, and season in a day. And normal pages are started after the series starts. This is an example from Lostpedia for a character named Kate Austin. You see here, you can barely see it. This is the first episode. And you see all of this red here are those pre-archived spoiler areas stacking on top of each other. And so you have a lot of area here where you can have a spoiler. And then you have archive extant spoiler areas that occur after archiving is started. We also have wiki before show pages that are started prior to the first episode. Yes, surprisingly, the first episode hasn't aired, but there's already a wiki for it. This is for a character named Daenerys Targaryen, which is in Game of Thrones, and there was a book series for Game of Thrones, so a bunch of enterprising fans knew the show was coming out and came up with the wiki. The interesting thing to us in this study is that you see a lot of archive extant spoiler areas, because there are no pre-archive spoiler areas. And then finally, we have season in a day pages. You have many episodes, but they all come out on one day. And a lot of Netflix series are like this. In this case, we chose House of Cards. And we'll talk more about this in a minute because this is a special case. So for normal pages, we see a variety of probabilities, anywhere from 0.15 to 0.67 for spoilers in a given page. For wiki before show pages, we also see a variety of probabilities. But for season in a day pages, our model breaks down. The reason is that you see how you have no probability of a spoiler, but yet you have 13 spoiler areas. Remember the graphic that had the single line? Well, the thing is that line is it's 0 in length. It's actually a spoiler area that's of length 0. So the point is that our model is breaking down because we can't use time as a dimension to differentiate between the individual episodes anymore. We need another dimension to work with, another model. So, also interestingly enough, the probabilities don't seem to follow any known distribution. And 50% of the pages have a spoiler probability of less than 0.66. And remember those missed updates we talked about? They're not being archived by the web archive? Well, we actually got to study those too. So each of these lines here represents a timeline for a given page. And you see at the bottom, time on the x-axis, and on the y-axis, you just have something representing each page. So you see the earlier pages started here, and and keep going to the right, and then more recent pages start up here. The color of the time, or the color of the line here, the darker colors indicate that there are more missed updates than the lighter colors. Now, I'm sure you'll notice it's getting lighter, which is good. That means the web archive is actually archiving more than it used to. You can even see these lines where the web archive changed its policy to archive faster, better. Now, on the flip side of that, we were wondering, well, is it archiving more? Is it getting redundant mementos? Is it recording the same page over and over and over again? And we see that the colors in this graph, the darker means that there are more redundant mementos. And so you can see the same lines, but it gets darker in the same place than was lighter over here. So the missed updates problem is going away, but we also have more redundant archives, which is actually not a bad, that's not bad, because the more copies you have, the better chance you have of not losing something. The librarians and others, there's some folks at Stanford, they refer to this as loss of copies, keeping stuff safe. And also remember that 38% of the pages don't have mementos, so this doesn't reflect all archived pages. So
go back, but there's a trade-off here.
Yes, there is a trade-off here. You see that the basically by increasing the number of the level of archiving, the intensity of archiving, you're avoiding missed updates, but you're having more redundant mementos.
There's a trade-off here as well. We're archiving some pages a lot.
That is true, yes.
And some pages not at all.
That's true, which that's another interesting study too. And so now that we've shown that TimeGates using min-dist are not quite good enough for avoiding spoilers, what about the Wayback Machine? Well, we actually had access to some anonymized logs from the Wayback Machine. And from these logs, we have which memento the user came from, which we refer to as the refer, and then the memento that the user actually gets redirected to. And what's interesting about the Wayback Machine is that when the HTML is sent to you as the user, the links are rewritten so that when you click on them, you end up at other pages all kind of in the same time period. There's also redirects that are in play as well. And so using this information, you can see that these individual URIs actually have the date time in them when they were recorded. So from this, using the refer, we can infer the desired date time that the user had, i.e. when they wanted to get to, and then we can also determine where they ended up. And using that information, we can take the Wayback logs, we can bounce them off of revisions from Wiki export pages, get the date time of the revision, and then the desired date time that we inferred, and then answer the question of, did the Wayback Machine redirect the user to the future, spoiler, or the past? And we found out that 19% of the requests in our sample ended up getting directed to the future. So 19% of the requests were spoilers. Now this is just for wikia.com sites. We actually don't have a way to identify all wikis on the web, so we were just restricted to that. So Wayback Machine can't help you. The TimeGates most of them are using min-dist, which occasionally results in spoilers. So we came up with a solution in the Memento MediaWiki extension. And using the Memento MediaWiki extension, we implemented minpast, because creating an extension for MediaWiki, we were able to control the implementation of the TimeGate. And so, before I continue, MediaWiki is the software used by Wikipedia and wikia.com. And that's why we targeted it. And so we set up a demonstration wiki at this URI, and we acquired the data from a website devoted to A Song of Ice and Fire, which is the book series behind the Game of Thrones. It was called A Wiki of Ice and Fire. And this gave us an interesting opportunity because we were able to make our own TimeGate using minpast. We could go ahead and compare different TimeGate patterns. And so, on the one hand, A new potential memento pattern we could use was this toRequest pattern, whereby you ask the original resource for to redirect you to a memento, and it already knows everything about all of its archived pages. So it only results in 2 requests. We expected this to perform much better. This was an opportunity for us to cut out one of the requests and save people some time. And then there's the traditional pattern that I showed you earlier, which has 3 requests. It should perform worse. And what we found, at least in the case of MediaWiki, was the opposite. With this 2 request pattern, MediaWiki takes too long to generate a TimeGate response if the 2 are on the same page. And this is because it's got to load the content of the page, and then it returns control to the extension to generate the TimeGate response. However, the 2 request pattern does perform better if you have about a 22 kilobit connection to the kilobit connection to the internet, or worse. And I did some research and found out that the average for the web or for the internet right now is in the megabits. It's not in the kilobits anymore. So there are very few people that would benefit from having the 2 request pattern. We were also able to use Siege to test the actual wiki article pages and see, did installing our extension affect performance poorly? And so if you look at this visualization here, each of these little circles represents the difference between the time it takes to make a request for the page with the extension installed versus the page without the extension installed. And what we were looking for was what we got. I'm very happy with the response or the results, because everything, for the most part, is around the 0, meaning we have little to no impact. If everything ended up here, it would be much worse, or down here, strangely, installing the extension makes MediaWiki work better. Neither of those occurred. We had minimal impact to MediaWiki, which should be good news for adopters. Also, looking at old pages or mementos in the extension, we see the same pattern. So installing the extension does not affect your ability to use MediaWiki. We also did a comparison between time maps and those MediaWiki history pages I was showing you earlier, and found that MediaWiki history or time maps are far smaller, so they perform better when you request them. And so MediaWiki doesn't just store previous revisions of pages. It also stores previous revisions of style sheets, JavaScript, and images. And so knowing this, we were wondering, well, what if the images could contain spoilers? Now this doesn't happen that much, to be honest. Usually people will upload a different image file for something else, and they won't keep changing the same image file to represent something. However, we did find an example where this was occurring. On Wikipedia, you have this article about same-sex marriage law in the United States by state. Now, this map is important to understand the content of the article. This image is changed as the content of the article is changed. So, why is it that when I go to the June 5th, 2013 version of this article, the text reflects the past, but the map doesn't? What we got was this map. What we should have gotten was this map. As you can see, California, and the colors represent different laws in different states. And so you see that California here has a very different color than it does now. In fact, they look very different. So if you're trying to research how this issue changed in the past, you're going to be confused because you'll be looking at the wrong map going with the article. And we were able to actually fix this in MediaWiki because we had an extension, we had access to all of the prior revisions. And so we used this function, this hook in MediaWiki to solve that. However, even though we were able to see the style sheets and the JavaScript from the user perspective, the extension doesn't have any access to that information, so we weren't able to solve it for style sheets or JavaScript. So we went to WikiCon USA 2014, and we did a little demonstration on avoiding spoilers. So consider this page here. This is our demonstration wiki for a character named Kevin Lannister, who is a character from Game of Thrones. And you'll see the nice thing about this particular wiki page is the folks who wrote it have a section for each book that is in the Song of Ice and Fire series. Now say I have not read A Dance with Dragons, but I still want to use this page.
Make the text bigger.
Oh, okay. So you see here, it's got a whole section devoted to the book A Dance with Dragons. So what we can do is, we can use the Memento for Chrome extension to select a date time prior to the release of that book. In this case, June 30th, 2011. And we can right-click and choose that date. And what the Memento for Chrome extension is doing is, it's going and talking to the Memento MediaWiki extension, the negotiating and picking up the Memento and redirecting it and so on. And you'll see that this page here has no reference to A Dance with Dragons. So we've avoided spoilers for this page. I'm sorry? That's true. There is also a bug, or there's also a spoiler in the latest page. I have a slide for that. Where you see the latest page says was. So if you hit the latest page first, you see a spoiler. So if you're in the previous page, the other nice thing about the Memento for Chrome extension, coupled with the Memento for MediaWiki extension, is you can right-click on a link in here, and let's go. And you can continue to browse the past. So you can continue to avoid spoilers. And so this was the state of Joffrey on June 11th, 2011, before A Dance with Dragons came out. And so there's the was. And this is a real problem, actually. The verb tense really surprises me. And so where do we go from here? Well, remember those Season in a Day series? Like House of Cards, Orange is the New Black. All the episodes for the season are released in a single day. So how do we handle that? Well, that's some future work that we or others can undertake. But what's interesting is there's this series called Arrested Development. And even though all of the episodes for the season were released all on a single day, like these other two, the latest season, not all the seasons, but the latest season, they can conceivably be watched in any order. And so now you have a philosophical conversation about what does it mean to have spoilers for that particular television show, specific to that season. You could also have that conversation about a variety of books that are all written in different chronological or, let's see, I guess in-story order. We're also considered, you can create a new heuristic for TimeGates, whereby you could look at the content if you end up in the future and see if it actually contains a spoiler, possibly using some machine learning or something like that. We also were considering using the extension to avoid spoilers for sports and the news. Say you hadn't seen the Super Bowl yet. And what about if you wanted to research what United States relations looked like before various agreements were announced, or before certain people came to visit Congress? How do we use min-future and min-past to study emerging topics on Wikipedia, like Cuban-United States relations? And we could also do further work on missed updates and redundant mementos. We just looked at the 15,000 plus wiki pages from Wikia, What would this look like from Wikipedia? What would this look like in different, I want to say, different locales on the planet? Are there some places where archiving is better than others? So these questions could be answered. And so we introduced the naive spoiler concept. Go ahead and select a revision prior to the episode you haven't seen, and you can go and you end up with a world where Joffrey is still alive. And as I showed you, you continue to right-click and end up in that time period. We've detailed TimeGate heuristics, and we've shown that minpast is the best out of the ones we've considered. We showed how to calculate the probability of encountering a spoiler. We actually calculated probabilities of encountering a spoiler and found out that it's not 0. So using regular Memento TimeGates, this is an issue. We showed that using the Wayback Machine, you still get spoilers. In fact, 19% of the requests in our data set actually showed spoilers. We developed the Memento MediaWiki extension to use minpast to help us avoid spoilers. But most importantly, we showed that it is possible to avoid spoilers in MediaWiki fan sites using Memento. Thank you.